I waited for around 15 minutes um, for the students to show up, but since nobody has shown up yet, I'll just go ahead with my with whatever I have to cover today. And yeah, so this will be as usual. This is uploaded on my YouTube channel, and anyone who's interested can review it at their own pace and time. So let's carry on. So today we are going to cover priority queuing with retrials, and geometric queues, queues with geometric distributions or discrete time queues. So, so here I have, and as I've mentioned earlier in my other previous sessions too, that I am not a maths department student. I'm not a queuing theory expert per se, but I use queuing theory for my research in networking. So there were some topics in the course that are kind of new to me, so I had to study them myself, and so that I can kind of help you guys out, help everyone out. So there were a couple of topics in this week's content that I had to go through myself, and I've prepared my own notes for them, and as I've been doing for the past weeks, I'll make this available, and you can review at your time. So I hope this will help you. So while priority queuing was something that I was fairly familiar with, queues with retrials is something that I had to go through. So I have my own notes here, which might help students. So I've kept it here. And the second topic was discrete time queue. And so this kind of a treatment was also new to me, geometric queues and the analogy with MM1 queues. So yeah, that I also have notes for geometric queues over here, where you have most of the main formulae and notations, derivations summarized. Okay, so let's solve some problems. We'll start with discrete time queues, or the GO queues, some problems based on that, right? So I don't really want to go over the theory again, but the basic concept of GO queues is when we have discrete time queues, that is when you don't have a continuous stream of packets or people coming in at a certain arrival rate and certain service rate, but they're coming in kind of chunks at certain distinct time intervals, which are discrete. So there, the analogous distribution to the Poisson processes in the continuous domain is the geometric process in the discrete domain. So the geo, that's why we study geo queues with a single server, and so that's the way of treating these queues becomes quite analogous to MM1 queues, and hence it's kind of very it's a good starting point. As mentioned by Professor in his lecture, there will be no further discussion on discrete time queues because anything beyond this gets really mathematically involved. So in GO1 queues, you can have two kinds of modes. One is early arrival servers, I think. So when arrivals come right at the beginning of the slot here, as I've shown here. And the second one is late arrival service, when the arrival comes right towards the end of the slot or just before the beginning of the next slot. So that's kind of the difference, and that changes a lot of the analysis that goes on. Okay, so but after all, these derivations can be done. But let's get to the problems. So the first problem is, again, I'll just write down the topic first. So we are doing geo 1 Qs, right? And then there are two kinds, LAS and EAS, right? So the first problem is for an LAS queuing system. So we have an LAS queuing system where the arrival rate is, mean arrival rate is something like 0.3, and the mean service rate is, let's say, 0.4, right? Let's make it 0.6. Just picking arbitrary numbers as usual. And so what we need to find out is the mean queue length, or LQ, right? This is just the mean queue length, or the average number of customers in the queue at any random time. And so how do we calculate that? So for this, you can check the notes. For LAS, there is a standard formula. It's there in professor's course, professor lecture 27. So this is one lecture 27, right? LQ equal to lambda bar by mu minus lambda times lambda by mu, and where lambda bar is nothing but 1 minus lambda, mu bar is 1 minus mu. So mu bar doesn't feature in this formula, but in general it features in some other formula. So then this can be calculated simply, right? It will be 0.3 times 0.7 divided by mu, which is 0.6 minus 0.3, which is 0.3 again, times 0.3 divided by 0.6. So this is 0.7 times half. So this comes out to be 0.35. That's the answer. You can solve similar problems. I hope I was right. Yes. 0.21 by 2. It's 0.7 but divided by 2 is 0.35. Okay. So the second problem that we can possibly solve is, same question, let's say, but with EAS, right? EAS. Okay. Same question with EAS, lambda 0.3, mu 0.6. So let's, so yes, this is the formula for LAS, and for EAS, we are giving, let's say, these two values, and let's take some other value actually. 0.4, mu equal to 0.8, and I want to find out probability that system is empty, which means that I can serve a packet. So then, if we check the notes, so that is nothing but if you derive the steady state probabilities and all. So what we really want to find out here is pi 0, right? Probability when the system is empty. So pi 0 is given by this quantity called 1 minus alpha where alpha is equal to lambda mu bar by mu lambda bar. And we know mu bar is 1 minus mu, lambda bar is 1 minus lambda. So this will be 0.4 times 0.2 divided by 0.8 times 0.6, right? So this I think is coming to be 1 by 6. So then this leaves us with pi naught equal to 1 minus 1 by 6, which is 5 by 6. So this is the probability that the system is empty. Okay. I'll just take a short break here. I'll come back in 2 minutes. Hello. Apologies for the disruption. But yeah, okay, I'm back. And so now let's do I'm kind of going in the reverse order. Because I believe the later topics really, that is the queues with retrials and the GeoGeo queues, are the problems that you can have from these kind of topics will primarily be just direct application of the formulae that you do. And yes, so the other problems such as the derivations and all are something that you really need to go through the lectures for it. They are not good for exam papers. But okay, so let's do a couple of problems on M1 queues with retrials, right? Okay. So on top of the usual lambda and mu in MM1 queues, we have this factor called gamma, which is the kind of impatience factor or the retrial rate. Okay. And so let's say we have a system where something like a call center, call center, let's say call center, problem number 3, and we are having calls at rates something like lambda equal to 50. Yeah, why not, like 30 calls per hour, right? And the service rate is of the call center facility is something like 60 calls per hour. So the call center facility can handle 60 calls per hour. And so there might be cases where the customer has a wait time and this just drops out and then makes another attempt for a call. So the retrial rate, gamma is given as like 6 calls per hour. And so there are 6 customers who will kind of call again after not being served. So that's kind of common for a call center, isn't it? So what we really want to find out is the average call waiting time. Right. So as for the notation used in the lecture, we have we denote this quantity as W naught, right? Average waiting time. And this is nothing but the average number of customers waiting divided by lambda according to Little's law, right? And we know lambda, we have to find out L naught here. So L naught is given by, now we can kind of refer to the lecture for this, something like L naught is rho square by 1 minus rho times mu plus gamma by gamma. That's the formula, right? So again, it's just a direct application of the formula. So it's rho square by 1 minus rho mu plus gamma by gamma, where rho is nothing but lambda by mu, which is half. So then this comes out to be 1 by 4 divided by half times 66 divided by 66 divided by 6, right? So that's nothing but 11. 1 by 4 by half is half times 11, which is 5.5 customers are waiting in the queue. And then so L, the waiting time will be nothing but 5.5 divided by 30. This will come out to be roughly 1.8. Yeah, 1.8333. So it's roughly like 0.183 hours. That's the waiting time. And you can convert this into minutes and other units, right? I have arbitrary numbers here, so I don't. Yeah, so this is actually, let's just write it in hours. So this is in hours. So in minutes, it will be this time 60, which is 11 minutes, right? 11 minutes. So this is a useful kind of quantity to know, because when you're calling to a call center, you need to know how much time you need to wait. Otherwise, you'll just wait. Otherwise, it's not efficient, right? Similarly, with the same kind of a follow-up to 3. So I'll just write it here. Follow up to 3. So you have the same numbers and all. So average rate of calls per hour. So you are asked what is the average rate of calls per hour? The average number of calls that are made per hour. So then how do we compute this? So remember that so you have 2 ways of calling. One, so this, let me write down the answer kind of. So average call rate, or in any other queuing system, I'm just using a particular use case. So you have one set of calls that arrive. So these are fresh calls. And then on top of it, you have calls that are because of retrials. So customers who drop out and then try again. So then that will be a fraction of the customers waiting in the queue, right? And that fraction is known to be gamma, the retrial rate. So this can be computed. And this is per hour. So yeah. So then lambda is 30 calls per hour plus gamma is I believe 6 times L naught, which is 5.5. And so this will be 5.5, 11, 33. I believe this is 63. So you actually have a higher number of redialing calls than actual fresh calls. So yeah, this is kind of one kind of problem that you can expect. And then the same question again. So I'll just write it again as follow-up. 2, 3. So we'll have the same numbers. So what we really want to find out is fraction of call attempts that receive busy signal, right? So we know that the total, so we know the denominator, which is lambda plus gamma L naught. That is nothing but the total number of calls per hour. And this is obtained in part 4, in question 4, right? So we have already obtained this. Now we have to find the numerator, which is, now this is something like total successful call attempts. And this is because the property of queues with retrials of the faster property that it's identical. So whenever there is a busy signal, it means that there has been a successful attempt just before it. And mathematically, you can show that these two quantities will be the same. So like this, you can check the notes from this for this system. This is what we have, right? This balance equation here is that when you have two possible situations, you have 0, you have 1. 0 is when the server is free, 1 is when the server is busy. So whenever the server is free and there is either an arrival or an impatient customer doing a retrial, you move into the busy state. So and if that attempt is successful, move into the busy state. So that's exactly what happens, and then you can just find whatever quantity you want to from that result. So that numerator is really, you can either write it as equal to 0 to infinity lambda plus n times gamma p0 comma n, that is the system is busy and there is a successful arrival or retrial, and then from the balance equation as I showed, it is right, it is also mu times p1 comma n. Now this is from the balance equation. Now here there's another thing. P1 comma n P1, so we have this quantity P of Z, right? P1 of Z equal to summation P1 comma n Z to the power n equal to 0 to infinity. This is the probability generating function, right? And from the lecture notes here, we have this result that P1 of 1 is rho. Rho is lambda by mu. So here we have P1 of 1 equal to rho, where rho equal to lambda by mu. And so this implies the numerator is nothing but mu times. And so rho, so and then note that P1 of 1 is nothing but summation n equal to 0 to infinity. P1 comma n, which is exactly the quantity that is in the numerator. So this implies that numerator is nothing but mu times P1 comma P1 of 1. So here you're putting z equal to 1. It is mu times P1 of 1. P1 of 1 is rho. Rho is lambda by mu. So you'll have mu times rho, and rho is lambda by mu. So this becomes just lambda. So therefore, this is the fraction of mu. So let's say this fraction receiving busy signal is nothing but numerator, which is lambda divided by lambda plus gamma L0. And the rest is this calculation, right? So L0 is already obtained in part 3. So L0 is 5.5. So, and lambda is 30, mu is 60. So it's 30 by, actually the denominator has already been obtained in part 4. So we can pick the value from there, which is 63. So it's 30 by 63. And so the answer is 10 by 21. Slightly less than 0.5. So pretty high percentage. So I hope this is clear. I see nobody has joined still, so I'll just continue with some other problems and then I'll end the call. Okay, so now we'll do some problems on priority queuing. Right. So we can have here two kinds of service, non-preemptive and preemptive. Right. So let's do some quick conceptual questions. So this is 5, 6. So let's say we have an MM1 queuing system, right? 1 second. MM1 queuing with priorities. Right. And so here we have, let's say, two priorities. So there is lower priority and higher priority. And the question is the PDF of, let's say, W0, the lower priority, is it same as the PDF of the higher priority, which is W1? So the PDF of waiting time. Waiting time. Is this PDF the same? And the answer here is no, because lower priority customers have to lower priority waits longer, right? So inevitably, if higher priority customers come in, the lower priority customers are pushed behind, and so even the mean waiting time is longer. So the PDFs can never be the same. Even if they belong to the same family, they cannot be exactly the same. Similar conceptual question. Can we, for the same, like, I'll just write it as follow-up of question 6. So is this true? That is the average, this is average customers rating in higher priority queue, and this is average in low priority queue. And so can we really say this? And the answer is again no, because we don't know the arrival rates. This is not provided. And so while it is almost guaranteed that if if there is a lower priority customer, it will have to wait longer. But we don't know how many lower priority and high priority customers are coming. Um, so we really don't know the arrival rate. So we cannot make any conclusion as to the number of customers that are waiting. Right. Now let's move on to some slightly more numerical problems. And so the first problem that I'll solve is something whose solution I've uploaded separately as a PDF as well. But I'll cover it in this kind of recording as well. So just a second. Yeah. So we have a priority queuing system. And so we have with two different service rates, mu1, mu2, and let's say and so it's a priority queuing system. So the serving rate 1 by mu1 is less than 1 by mu2. So first priority 1 greater than 2. Priority order is 1 followed by 2, something like that, right? And let's really set up. So we have, and so let's assume that the arrival rates can be in general different, but for now, let's assume that the arrival rates are the same for both processes, and it's denoted by lambda. It just makes your derivation a bit easier. So I'll go ahead with this. But I'll just write it down. Try with different arrival rates, right? So that's something I am leaving it for you. Okay, so again, what am I trying to do? So I can have essentially two kinds of priority orders. So I have the service rate of 1 is less than 2. And so I can have two kinds of priority orders, right? I can have priority orders 1, 2, and also 2, 1, right? And so what I really want to find out is which of these two priority orders has lower wait time. It's a decision to be taken, right? So I have two class of services. One of them is faster than the other. One of two class of customers. One of them can be served faster than the other. So what priority order I should be following? This actually is a very neat derivation. And let's write down for case 1, which is when priority order is 1, 2. So then the wait time, we'll use the notation in the lecture, which is for the higher priority customers, which is wait time for actually let me put these as case A and case B, right? So wait time for case A for the first customer is nothing but 1 by mu1 divided by 1 minus row 1, right? And here row 1 equal to lambda 1 by mu 1 equal to lambda by mu 1, and row 2 equal to lambda 2 by mu 2 equal to lambda by mu 2, right? Because our regular rates are the same. And so, and then you have for the second category, which is W2A, you have 1 by mu 1 divided by 1 minus row 2 minus row 1 plus, because you have to wait for the first category. And then you have a row 2 by mu 2 divided by 1 minus row 2, 1 minus row 2 minus row 1. Okay. Now, so in the case B, you have W1B equal to my bad. For the second case, this will be actually, so this is the second class of customers, right? So they'll be doing their own service. So this will be the formula. First, this is for their own waiting time for customers of class 2, and then this is the waiting time for customers of class 1. And then this is how the formula changes as well. Right. And again, for the case B, we have the first kind of customers will actually have to wait longer. So for their own case, they wait 1 minus. And then for the others, it is for the other priority customer, because here, remember here, 1 is lower priority. So these are just textbook formulae, writing them down. And then W2B is nothing but right. And so let's now find out the average waiting time, right? In both. So in the situation A, the average waiting time for both customers is nothing but lambda 1 times waiting time for customers of class 1 plus lambda 2 times waiting time for customers of type 2 divided by lambda 1 plus lambda 2. And we know that, so this will be nothing but half times since lambda 1 equal to lambda 2 equal to lambda. So lambda will cancel, and so this is what we'll have. Now we can just substitute the values from here, but let's not do that right away. And the waiting time for category B will be lambda 1 times and to a similar argument, we can write it as W1B plus W2P, right? And so then again, using the assumption that they have the same arrival rates, now what we really want to find out here is this quantity WA minus WB. We want to find out which is greater. So let's take the difference. So this will be nothing but half times W1A minus W1B plus half times W2A minus W2B. Right? Let's compute these two quantities really quickly. Equal to, so firstly 1 by mu1 times 1 by 1 minus rho 1 minus okay. So if we take things common and all that, so what we'll first have is we have something like this minus rho 2 1 by mu1 plus minus rho 2 1 by mu1 plus 1 by mu2 divided by, actually no, I'm wrong. So it will be something like minus rho 2 by mu1 times 1 minus rho 1 1 minus rho 2 minus rho 1. So that will be the first term. And then, yeah, minus. And then the second term will be minus rho 2 by mu2 divided by 1 minus rho 2. Yeah. So now let's move on to the second class of customers, which is again a similar kind of formula that we'll get. Okay. Now, if we just kind of break down the terms, so this is what it will come to. So 1 by mu2 and so now we know that this rho 2 is lambda by mu2. So probably that doesn't help us with it. Let's just carry on. And so what we want finally is this quantity, right? WA minus WB. So let's just put this in. Half times sum of these two things, right? W1 A minus WB. Let's add these two, which is minus rho 2 by mu 1 by 1 minus rho 1, 1 minus rho 2 minus rho 1 minus rho 2 by mu 2, 1 minus rho 2, 1 minus rho 2 minus rho 1 plus rho 1 by mu 2, 1 minus rho 2, 1 minus rho 1 minus rho 2 plus rho 1 by mu 1 by 1 minus rho 1, 1 minus rho 1 minus rho 2, right? So now let's just multiply and divide both sides by lambda. So this was half, so we can write it as lambda divided by 2 lambda. And so lambda by mu 1 is rho 1 and lambda by mu 2 is rho 2. So this just becomes 1 by 2 lambda times minus rho 1 rho 2 by 1 minus rho 1, 1 minus rho 2 minus rho 1. Again, minus over rho 2 minus rho 1 rho 2 once again. Sorry, it will be, I believe, minus rho 2 squared divided by 1 minus rho 2, 1 minus rho 2 minus rho 1 plus rho 1 rho 2, 1 minus rho 2, 1 minus rho 1 minus rho 2 plus rho 1 squared divided by 1, 1 minus rho 1 minus rho 2. So if we simplify further, this will give us rho 1 rho 2 divided by 1 minus rho 1 times 1 minus rho 2 times 1 minus rho 1 minus rho 2, and this whole thing multiplied by 1 minus rho 1 minus 1 plus rho 2. So if we essentially just sum this term and this term, right? Okay, so 1 and 1 get cancelled. Anyway, let's continue. And then the other term is nothing but, again, 1 minus rho 1, 1 minus rho 2, 1 minus rho 1 minus rho 2. So if you essentially take this term and this term together, so we'll have rho 1 square times 1 minus rho 1. My bad, rho 1 square times 1 minus rho 2 minus rho 2 squared by 1 minus rho 1. Right? So if we do a little bit of simplification, what we'll get here is 1 by 2 lambda. So let's just take this whole factor out. 2 lambda 1 minus rho 1 1 minus rho 2, 1 minus rho 1 minus rho 2. And then we'll have something like rho 1, rho 2, rho 2 minus rho 1 plus, and let's just break it down completely, rho 1, rho 2 squared minus rho 1 squared, rho 2 plus rho 1 squared minus rho 1 squared, rho 2 minus rho 2 squared plus rho 1, rho 2 squared. Right. Yeah, this derivation is a bit long, but thought I'll do one of this kind of question anyway. So then this simplifies to rho 1, rho 2. Let's just add these two, right? So we'll have rho 1, if you take these two as common, rho 1 square and rho 2 square. So we have rho 1 plus rho 2 times rho 1 minus rho 2. That is, if you take these two together. And then for the other two, we'll have plus 2 rho 1, rho 2 minus 2 rho 1, rho 2, right? Rho 1 minus rho 2. Rho 1 minus rho 2. And then, of course, the whole thing is divided by this quantity. And so if you take everything together, you'll get something like rho 1 minus rho 2 times rho 1, 1 minus rho 2 plus rho 2 times 1 minus rho 1. We'll get something like this, rho 1 plus rho 2 minus 2 rho 1 rho 2. So that you can break it in this way. And then the denominator term. Right, so here we have lambda greater than 0 for sure. And then we have rho 1 and rho 2 are both less than 1, right? And to be more precise, it's between 0 and 1, which means 1 minus rho 1, 1 minus rho 2 are all greater than 0. So then, and then the third criteria that we have is total utilization has to be less than 1. So we'll always have rho 1 plus rho 2 less than 1, which gives us 1 minus rho 1 plus rho 2 greater than 0, right? So we have the entire denominator is greater than 0, and this term is also greater than 0 in the numerator. And so that leaves us with rho 1 minus rho 2. Let's evaluate that. Rho 1 minus rho 2 is nothing but lambda 1 by mu 1 minus lambda 2 by mu 2. And let's say we call that lambda. We have been operating under the assumption that's lambda 1 and lambda 2 are equal, right? So we have lambda by mu 1 minus lambda by mu 2. So it's lambda by times minus 1 by mu 2. And so by our previous assumption that, like at the very beginning of the question, that the first class of customer is served faster. So we have 1 by mu 1 less than 1 by mu 2. I can write it by assumption or like is given rather. So this is given, which implies rho 1 minus rho 2 is less than 0. And this is what determines the sign of this whole quantity. So because the other terms are positive, so we'll have WA minus WB is less than 0. And this brings us to our final result, which is W type A is less than variant time of type B. Right? So then this, so then the preferred, I can write them out like this, preferable to serve faster customers. That's the kind of intuitive idea, but this derivation shows you that it's preferable to give higher priority to the customers that can be served faster to reduce your overall wait time. This is from queuing theory analysis. You can end up obtain this result. Right. Okay. And this is like irrespective of the values, but in general, if you have to, like for particular cases, if lambda 1 and lambda 2 are different, then you might have to actually calculate the values and show this, but this is a useful proof to go through. So I thought I'll cover it. So I'll solve two problems from the book Butsekas and Gallagher. I've uploaded the textbook and the solutions online in the drive link. And so just give me a minute. Actually, let's just solve one problem because we haven't covered MG1Qs yet. So let's just stick to MM1Qs. And so the question here, so it is problem number, so I'm writing as Butsekas and Gallagher, problem 3.40. This is from chapter 3 of Butsekas and Gallagher. It's from the 40. And so what is the problem here? So the title of the problem is optimization of class ordering in a non-preemptive queuing system. Right. So the first part of the problem is, let's say part 1 or part A, is you're being asked to show that this sum, which is k equal to 1 to n, rho k, wk, this is independent of priority order. So no matter what your priority order is among these n customers, this sum where kind of the the sum is like, so here, and then so, and the formula for this quantity is actually residual times. Actually, I'll still cover this problem, but this, I'll just make a note here that this uses results from MG1, which comes in later. But I'll just quickly solve this kind of this quick result that, and so you can try deriving it for an MM1, but it holds for MG1, so also holds for MM1, right? Because we're not really looking at the service distribution here. So you can really solve it by induction. So for any W, so the first one is really W1 is a non-preemptive service. It is W1 is nothing but so in general, we have this formula, right? Wk equal to R by 1 minus rho 1 minus rho k minus 1. One minus rho 1 rho k, right? So right. So let's say for a simple case, so if you like, let's assume that it's true for let's assume that this is true for step k, right? So we actually have this result rho 1 plus rho k. So now the next step in the induction is to show it for k plus 1, right? So we assume this is true and then we solve for this. And so this actually, if you do the algebra, kind of skipping the details here, you'll actually kind of get the same result, which is, so you just have to add this rho 1 plus to add to this this formula, right? Times the waiting time. So the formula is R by, let's just write it properly, rho k plus 1 times R divided by 1 minus rho 1 rho k 1 minus rho 1 rho k plus 1, right? So if we sum these up, and what we'll have here is again, if we will have R times row 1 plus row k plus row times, so this row 1 plus row k times 1 minus row 1 times row k plus 1 divided by and then again plus row k plus 1 times R times and this whole quantity is divided by 1 minus row 1 to row k 1 minus row 1 to row k plus 1, right? So if we add everything up, we'll have R times row 1 plus row k plus 1. And then we'll have, so then this quantity is nothing but row minus, we'll have something like row 1 plus row k plus 1 times row 1 plus row k. And then this is again row R, right? And then in the numerator, in the denominator, we have this. And yeah, so if we take R times row as common, we'll have 1 minus row 1 row k, so then we already have this term in the denominator and row k plus 1. And so these really cancel out. And so what we have is right. So then not this, again, it's the same quantity. So the induction hypothesis is proved, and so the whole argument is proved. So this was one problem that I wanted to discuss. So that's it for today. And, see you next class. I would have waited if there was any student coming in, but yeah, I'll just share the notes. Okay.